Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss something known as PCIe Configuration Space and Base Address Registers. This is very important to understand so that in future when we are discussing about the transaction layer packet or the PCIe packet, we are going to come to know how this particular configuration space is useful and how the base address registers and are all useful. Now, first of all, let us try to understand what is a configuration space. So basically, a configuration space is nothing but it's a kind of address registers or a kind of memory which is present inside a particular PCIe function. Okay. Now, what is a PCIe function? First of all, let us try to understand what is a PCIe function and let us come back to this definition of configuration space. Now, basically, a function is one independent addressable worker living inside a single PCIe device. For example, if I'm going to have a PCIe compliant combo card, okay, this particular PCIe device can have multiple functionalities. One of the functionality is function 0, which is nothing but acting as a network controller. So this is one functionality. So this particular PCIe card can act as a network controller. So it is going to appear as an Ethernet adapter and with its own vendor device ID and BAR. So when my OS is going to access this particular PCIe, it is when my OS is going to access this particular PCIe device, it is going to access this particular functions and it is going to come to know what are the different functionalities I'm going to have. And one of the function, it is going to come to know that it can act as a network controller. My chip can act as a network controller, and the other functionality is storage controller. So like this, a particular PCIe chip, a single PCIe card can have multiple functions which is present in it. Now here, each function is going to have its own configuration space. So that is nothing but my function. Okay. Now, what is meant by configuration space? Configuration space is nothing but it's a set of registers where it's a kind of set of memory. It is where it is going to contain the information like vendor ID, device ID, class code, revision ID, command register, status register, BAR, capability list. All the information will be present inside this particular configuration space. So each particular PCIe card for each particular function, you are going, let's say suppose if I have multiple functionalities like this 1, 2, 3, and 4. So each function is going to have its own configuration space. So whenever you are inserting this particular chip into the PCIe slot, then the OS is going to come to know about entirely about this particular chip. So for knowing about this particular chip to the OS, what we are going to do is we are going to have a physically implemented configuration chip inside a particular chip. Okay, and inside a physical chip, and each particular function is going to have its own dedicated configuration space. So that is what it is written over here. So a fixed set of hardware registers implemented inside every PCIe function, and it's not the device memory used for the data transfer, and it is used mainly during PCIe enumeration by the OS. And this is what we have seen in our previous session also. What do I mean by enumeration? Okay, so in the enumeration phase, my OS is going to basically use it and use this particular configuration space. Okay, now so this is the pictorial representation of what exactly your function is going to have. So each function is fully independent and its own configuration space, bar, and control status register. So if I have three functionalities, each function is going to have its own dedicated configuration space. Now, so inside the configuration space, as I've told you, I'm going to have multiple informations like vendor ID to header type and all the informations I'm going to have. And first of all, we are going to discuss and focus more upon this BAR, which basically stands for base address register. Okay, and then we will briefly see about the other kind of registers which I'm going to have. But the main important agenda and the focus of this particular session is discussing about this something known as BAR register or bar. Okay, now this particular register which will be present inside your configuration space. Okay, now this particular BAR stands for base address register, and it's a configuration space that tells the OS where should this device appear in CPU address space. Now what exactly is this line stating? Let us try to understand over here. Let's say suppose if I'm going to have a processor and a particular UART controller kind of device. Now, if I want to establish the communication between this processor and a UART controller, how I am going to establish? I can't say that a processor just start controlling UART. No, I cannot basically have the connection established like this. So, my processor is going to use something known as addresses. Okay, so there will be dedicated set of addresses which will be present for this UART. Let's say suppose from 0 to 64, just randomly I'm giving it. Okay, so using this dedicated set of addresses, my processor is going to communicate with my UART controller. My processor cannot exceed or it cannot go below the addresses which was specified for a specific set of controller. I can have multiple devices which are connected to my processor, and if my processor wants to communicate with any particular device, I am going to have a kind of set of fixed addresses which my processor is going to use for establish that particular connection. Now, who is going to provide this particular addresses to my controller, and how the processor is going to utilize this particular addresses, and how the processor is going to come to know what is the starting address and what exactly which address should be used. This is what the bar is used. Now, so it is not, the bar is not used to store the device registers. So the device data and all will not be stored inside your bar, and it is going to store a starting address. Okay, so bar is used for storing a particular UART controller or whatever the PCIe compliant device is there, right? That particular starting address, in this example, 0 will be stored inside your BAR. Now, who is going to provide this particular BAR? I'm providing here, for example, I'm giving 0, but who is going to provide the base address, and who is going to provide the base address is OS. So whenever our operating system discovers this particular device, it is going in the enumeration phase, and in the configuration it is going to update this particular bar with a dedicated base address, and this particular starting address will be stored inside your base address register. And I'm talking about a particular functionality. So a UART controller can have multiple functionalities. If, let's say, if it is only having one functionality, then it is going to store that particular base address inside this particular starting. Okay, now it is going to store that particular base address into this particular bar. Now, first of all, OS going to discover this particular controller during the enumeration phase, and during the configuration it is going to update this particular bar with the starting address. Now, whenever the processor wants to communicate with this particular UART controller, it is going to read this particular bar, and it is going to establish the communication with this particular UART controller. This is how the communication is going to be established between the processor and the controller. So you can see this particular example where I'm going to have, in this particular UART controller, I can have multiple registers. Okay, I can have a particular control register, I can have a status register, or I can have a transmitting register, or I can have a receiving register. Like this, I can have multiple registers which are present inside my uh, controller. Now, how the processor is going to know which particular register address is which? So you're going to have something known as two kind of addresses. One is base address. Base address is nothing but my starting address, which the processor is going to come to know from the register which is known as BAR, and this will be updated by the OS. OS is going to update this particular register. That is, it is nothing but my starting address. And the offset address is basically fixed. So I can see for the status register, I'm going to have the offset address is equal to 4, and transmitting register is also going to have the offset address as 4. So all the registers are going to have the offset address of 4. So if I want to access the status register, my processor is going to basically add my base address plus offset address, so that it is going to communicate or access or the configure this particular status register. And if it wants to access this particular transmitting register, TX register, my processor is going to add the base address plus the offset, which is nothing but 8. So like this, my processor is going to communicate with a dedicated registers. Now, you can see over here, so BAR assigned by the OS, which is nothing but this particular address, and using this address my processor is going to have the provide the particular address, and it is going to access those particular addresses like this. And this is how we are going to establish the communication between my processor and the controller or whatever the device using this particular configuration space. And the configuration space is going to have one such important register, which is known as bar, which is updated by the operating system during the enumeration and configuration space. And that is what we have discussed so far now. So why the bar is needed? So we are going to use this particular base address register when the OS is going to discover the device. It is going to read the base address register, and it is going to determine how much address space it is needed. This particular step we haven't discussed it yet, and we have discussed that it is going to discover it, it is going to read the bar, and it is going to allocate a particular base address. That is what we have discussed, right? So in this particular steps we have, it is going to discover the device, it is going to read the bar, and it is going to determine how much address space it is needed, and it is going to allocate a particular free memory range, and it is going to write the base address into the bar, and CPU is now going to access the device with that particular address. This is the step number 1. Step number 5 and step number 6 we have discussed it as far as now. Now, that is one functionality this particular base address register was having. What is the one functionality which we have discussed? It is going to store the base address which is being configured or updated by the operating system. That is what we have seen. Now, there is one more functionality also. What is that particular functionality? Now, bar register is also used for describing the OS, like how much space it needs. For example, in the UART controller, you can see I'm going to dedicate a 64 bits of data for this particular UART controller. Not bits of data, actually, when you're working, you're going to have some bytes of data. For example, if I'm going to allocate for this particular UART controller some 64 bytes of data. But how the OS is going to come to know how much space should be given to this particular UART controller? UART controller should describe to OS, right, like how exactly how much space it needs, whether it needs 32 bytes or 64 bytes, or how much bytes of data it basically needs as a space. That is also decided by the bar. Now, this will be decided by the bar. So from this we can come to know that bar has two functionalities. One is basically for storing the base address, and another is for deciding how much space it is going to require. Now let us try to understand how bar is basically useful for determining how much space my controller needs, and how controller is using bar for requesting OS for dedicating that particular number of space. Over here we can see, so how does OS knows how much space to give? So the bar doesn't just hold an address, that is what I was saying. It is also going to reveal the size of the region the function is going to require, and the OS finds this out with a simple probe called bar sizing procedure. So let us try to understand what is this particular bar sizing procedure. In the step number 1, OS is going to write all ones into this particular base address register. So software is going to write down all ones into the bar register, and every bit is set to 1. Now, OS is going to read back this particular bar register. Now, hardware doesn't actually store what was written. What it is going to do is it is going to bits the device that doesn't use for addressing snap back to 0, and only the bits above the region size stays 1. And OS is going to decode the size, and OS is going to write the real base address. Let us see this with one example so that it will be more clear. So in step number 1, you can see OS is going to write all ones into this particular bar. And step number 2, you can see device is returning this particular information. That is, first 4 bytes of data is written with FFF, and last it is going to return as F000. That means lower 12 bits are hardwired to 0. You can see this lower 12 bits are hardwired to 0, and device is going to ignore them. And after processor is going to read them, so it is going to invert everything, whatever the information which we have received, the software is going to invert them, so that this is my final result. To this it is going to add 1, which is nothing but 0, which is nothing but hexadecimal, this information, which is nothing but 4096 bytes or 4 KB. This is how my software is going to come to know what is the exact memory space my hardware is required. So let us see one more time. OS is going to write down all F, and device is going to return what how much space it exactly needs by basically flipping those particular bits to 0, and my particular software is going to invert everything, and it is going to add 1 so that it is going to come to know exact which how much space it basically needs, my hardware needs, so that it is going to allocate that much space for it, and after that OS is going to assign the base address into the bar. So this is how we are going to, my OS is basically providing 4 KB space to the device, as well as it is also updating the base address register. Now, in the in the case of my configuration space, it is basically a collection of hardware registers where bar is one of the register inside the configuration space, and configuration space is going to store the device information, whereas bar is going to basically store the base address assigned to the device, and configuration space is used during the enumeration, and bar is used to map the device registers into the CPU address space, and configuration space is going to have different kind of registers like vendor ID, device ID, BAR, and capability registers, and etc. Whereas bar is going to contain only the starting address of a memory or a input output region. Now let us try to understand different kind of header types in our PCIe. So basically, header type field in the configuration space. In the configuration space only, in the registers, which we are going to have one particular field which is known as header type. So if I can show you, this is my type 0 header type, and these are all the registers which I'm going to have, and you can see in this particular offset address C, in the offset address C, this is my entire configuration space. You can see this is my entire configuration space, and inside this configuration space in the offset address C, I'm going to have this particular field which is known as header type. This is going to basically decide what kind of header type it is. Now I can have two type of headers. One is type 0 header and another is type 1 header. So type 0 header is used by Ethernet controller or SSD or all the endpoints, which is nothing but uh, to the end of the hierarchy, what are the devices which we are going to have. Those particular endpoints are going to use this kind of headers, the type 0 headers. And basically type 1 headers are used by bridges, or bridges is nothing but in our PCIe we are not going to have any physical bridges. We are going to have switches, and we are going to have root ports. So those are all will be considered as virtual bridges, and those will be having type 1 header. Okay. Now, what is the difference between type 0 header and type 1 header? Type 0 header are going to have basically 6 bars, and it is going to have the information about interrupt. It is going to have expansion ROM, capability pointers, and all. And in the case of my type 1 header, it is only going to have 2 bars: primary bus number, secondary bus number, subordinate bus number, and different kind of informations. So you can see over here, this is the example for a type 0 header, where I'm going to have vendor ID, device ID, command status, revision ID, class code, cache line, latency, header type. Header type, if it is equal to 00, then it is a type 0 header. And BIST is nothing but built-in self-control, self-test, and I'm going to have total 6 bars over here and different kind of registers. So this is nothing but my type 0 header configuration space. In my type 0 header configuration space, these are all the registers which will be present inside my configuration space. Yeah. And regarding to this particular exact field details and all, we will have a separate discussion. But in this particular session, our main focus is to understand what exactly is configuration space and what exactly is bar. So a particular PCA function, it is going to have a configuration space, and in configuration space, I'm going to have something known as BAR, which is going to store the base address, and using this, it is going to map the device into CPU address space, and I'm going to have the different kind of headers, which is nothing but type 0 and type 1. And using type 0 header is going to have different kind of configuration space layout, and type 1 header is going to have different kind of configuration space layout. And type 0 configuration space layout just now we have seen. So this is nothing but my type 0 header configuration space, right? Yes. So that's about this particular session, and in our next session we are going to discuss what exactly type 0 header and what is exactly type 1 header, and what are the different kind of fields which we are going to have in a configuration space and all, we are going to discuss in great detail. Yes. So that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.